Hello, hi. It's me again. It has been like 3 months. I hope that I'm in frame. The setup of the camera is really weird. It has been like 3 months since I last uploaded. I still cannot sleep. My insomnia is haunting me. It is 3:45 a.m. right now. Okay. I've taken two melatonin gummies. They're not working. Melatonin. That has a cool structure. Want to see what it looks like? It's a benzene ring. I think it has an oxygen over here and a methyl group. And then it has something like this. God, please be correct. Uh, and then it goes something like this. Yeah, it looks something like this. Oh, I think it has this. Yeah, it has a double bond over here. So this is what melatonin looks like. Um, yeah, it makes you sleep. It's not working on me, obviously. Okay, I'll have to cut all of that out. I went on a rant about melatonin and how it reacts in our body, but that's not the aim of this video. It is organometallic. So let's get into that. Before starting organometallics, you need to know about carbonyls. If you know what carbonyls are, just skip to this timestamp. It's somewhere on the video. I hope I put it in while editing. So carbonyls. What are carbonyls? Carbonyls are C double bond O. Well, any compound that has C double bond O, it has a carbonyl group in it. Carbonyls are present in many functional groups. They are present in ketones, aldehydes, carboxylic acids, amides, in acyl chloride, and other acyls. You'll see this carbonyl group pop out a lot. So they're important and they're special. Why are they special? Because they take the shorter bus to school. No, they're special because of this polarity. Oxygen is more electronegative than this carbon, so it has a negative del charge, and this carbon has a positive del charge. So what happens is electrons tend to shift towards this oxygen. All right, so this carbon will act as a great electrophilic center. Electrophilic center meaning that it will act acidic, and by that I mean that it will, in any compound that has a carbonyl group in it, this will make it act like an electrophile. All right, so why is carbon such a good electrophile in this carbonyl group? Well, if you know about molecular orbitals and how they are made, you would know that when two atomic orbitals overlap, they form two molecular orbitals. One of them is ABMO and the other one is BMO, anti-bonding molecular orbital and the bonding molecular orbital. So if you put electrons in the bonding molecular orbital, a bond will form. If you put electrons in the anti-bonding molecular orbital, the bond will break. So if you had to see the sigma bonding molecular orbital, the orbital in which you have to put electrons to form the sigma bond, it would look something like this. It's really big or really dense towards the oxygen, and it's really small towards the carbon. This is the sigma bonding molecular orbital. So if you would want to form a sigma bond, you could attack this carbon, all right? Or you could say that this carbon has the tendency to form a sigma bond. If you want to break a bond, let's say a pi bond, why? Because pi bonds are easier to break. They are lower in energy than sigma bonds anti-BMO. So these pi star ABMO will look something like this. Is the oxygen, this is the carbon. It will be smaller on the oxygen and greater on the carbon. So if you would want to break the ABMO, the pi star, the pi bond, you would have to attack the carbon. Why? Because it's more dense. Well, it's not like you would have to attack it. The electrons would transfer to the pi star ABMO because it's easier for them. It takes less energy. So it will go into the carbon, and the carbon will help break the pi bond, and these electrons would shift to the sigma BMO. All right. So I'll show you what it looks like. That would be easier. So let's say we have a base. All right, bases are great nucleophiles. So If we want this base to react with this carbonyl, this is a ketone, acetone. I'll write this as R and R dash so you can imagine it to be whatever you want. It will attack this carbon. And where will these electrons go? In the pi star BMO, ABMO. All right? And this pi bond would break. Now this pi bond has 2 electrons. Where would these electrons go? Charges cannot be, destroyed, right? Before flying off into the air, this oxygen would attract them. Why? Because it's more electronegative. So these electrons would move up to the oxygen and it would form something like this. There will be a single sigma bond and these electrons are on the oxygen's p orbitals. So this will be the lone pair that it has and this will be the negative sign on it. So these are the electrons that were pulled on top of the oxygen. The R dash and R stays here and the base would now join this carbon that it attacked. So is the base. So this is what would form after we attack a carbonyl group. All you had to infer from this whole thing was how carbonyls react when they're in the presence of a base or a nucleophile. All right. First, it will attack the carbon, and the electrons in the pi bond would move over to the oxygen. This is all you had to know. All right. So let's talk about organometallics. So organometallics. Where should we start? Let's start at the carbon metal bond, all right, because it's all about bonds. Organic chemistry is about how you form bonds and how you break bonds, all right? So if you look at this, what do you see? You see lithium and you see carbon and you see 3 hydrogens. The thing is, just like the carbon and the oxygen that I told you, in this case, carbon is electronegative and the lithium is electropositive. And this is really polar towards the carbon. Well, just showing an arrow and making signs does not explain it a lot. It does not do it justice. So let me show you the LCAO linear combination of LCOA, like how? I don't know. Linear combination of atomic orbitals. I don't know. So this is the energy line. What happens is the 2s, lithium has its 2 bonding electron in the 2s orbital. Would be like this. And the carbon has 4 sp3 hybridized orbitals. They would be lower energy than 2s. So 1, 2, 3, 4. These are the sp3 orbitals. So if you look at CH3Li, we know that, okay, let's talk about just carbon. So the sp3 orbitals have 1 electron in each orbital. Since this is CH3, it will have 1, 2, 3. 3 electrons that are paired. Why are they paired? Because of the hydrogen. So let me label this as CH bonds. Okay? These are because of the CH bonds. Now what will happen is this electron and this electron would they would combine to form the CLI bond, sigma bond. This is the sigma star and this is the sigma BMO, okay? Now, this is all good. I want you guys to focus on this part, all right? If you look at it closely, let me make it into a box. If you look at it closely, I'll show it to you over here. You will see that, okay, just look at this, okay? You note it down or do whatever you want. If you look at this, we can see that it is like this. 1, 2, 3. So if you look at it, these 3 make up CH3 and this makes up CLI, all right? The thing is that this CH3 and this CLI are really close in energy. You can see that this has some X kJ of energy, this has some Y kJ of energy. These X and Y values are really close to each other. If you zoom out, they may look same. They may look the same, but they're not. So what happens is that this CH3 considers this CLI as a lone pair on it. Hence, this CLI bond is extremely carbonic. It shows a lot of carbon character. So this gives it an anionic character. All right, this gives the CH3 an anionic character. So you might see in different books they write CLI or CMG. Let's say there is 3 over here as CH3 negative. So if you were to be writing a chemical reaction, you can write it as CH3 minus or CH3 Li. If you wanted to show the electron moving from this to a electrophile, you could use the negative, or in this case, you would have to draw the arrow coming out from the bond. Why? Because these electrons are acting, these electrons are the ones that are in the CLI bond. So this is the one that is doing the attack. Lithium is not doing this. This is not doing the attack. These are not doing the attack. It is this. These are the ones that are attacking the nucleophile or the electrophile. So you would show it from the sigma bond. So that is how carbon and metal bonds work and how it will attack. Now let's move on to the next section. This was important. The only thing important about this was you should know why this works. All right. So just put this in mind. To keep this in mind, not put this in mind. Holy crap. Yeah, my English is really good, I know. All right. So now that we know how carbon metal bonds would give their electrons, let's see how we can make these carbon and metal bonds. All right. So the first reagent, the first organometallic reagent that we will learn how to make is called the Grignard's reagent. I hope you know what that is. Grignard's reagent is RMGX. I think I'll tell you about 1, 2, 3, 4, 5. 5 ways to make organometallic reagents. 3 of them are important. The less important ones I'll tell you at the end of the video in like a minute or so. So RMGX, this is the Grignard's reagent, all right? R is the carbon chain. It can be any carbon chain, alkane, alkyne, alkyl, whatever you want, all right? So carbon chain. X is the halogen. And Mg is magnesium. What else would it be? So how do we make this? Well, the reaction is something like this. Let's say I'll take 1, 2, 3, and I'll have an I to it. All right. This is a haloalkane. 1, 2, 3 propane and an iodine. So it's iodopropane. So what we'll do is we will make it react with magnesium turnings. All right. Mg turnings. If you don't know what turnings are, this is what they look like. So yeah, magnesium turnings. And we'll use a special solvent. And this solvent would be an ether. Why do we need an ether? Well, to stabilize the Grignard's reagent. Grignard's reagent or any organometallic reagent is an excellent base. It's extremely reactive, all right? We have to put them in black containers, I think, so that it would not react with light and break down. So to stabilize the product, we would need an ether. This ether can be ET2O or THF or DME, any one of these. I'll go with DHF and ET2O, all right? Just pick one. What will happen is this Mg would, all right, I'll show you. MgI. This is the formation. Now you might be wondering, what the fuck? You just showed me the reaction. What is the mechanism? The thing is, the mechanism is really debated because we still don't know how they work. What happens is there is an oxidative insertion. What the hell is an oxidative insertion? What happens essentially is this is the I. Magnesium here has the oxidation state of 0. This will insert itself between this and it will form this MgI. Here the magnesium's oxidation state is 2. So it went through an oxidation, so it is called an oxidative insertion. The mechanism is that I'm going to tell you is done by a free radical reaction. It is accepted in many places, but it is not the correct one. because we don't know what's happening in the actual reaction. So let's talk about the mechanism of this preparation. Let's take R and X. This is an alkane or any carbon chain. This is a halogen, all right? And then we'll make it react with magnesium in an ether solvent. So what will happen is this magnesium would give out 2 electrons. And since the halogen is more electronegative, it will attract the electrons towards itself, making this R a good electrophilic center. So this negative would attack this R, and X, being a good leaving group, would take these electrons and get out of the reaction. So they would look something like this. It will have an R minus. The Mg lost 2 electrons, so we would write Mg like this. And the X would have extra electrons, so X would have a negative on it. And if we combine these three, we get this will attack it here and this will attack it here. We would get R Mg X. Is it the same? Yes, it is. The thing is, the final product looks something like this. I'll show it to you. Yeah, it looks something like this. Why do we have these extra ORs? Well, because we used an ether to stabilize it. This is them stabilizing the Grignard's reagent. So this is what the final product would look like. Another thing about Grignard's reagent is that it catalyzes itself. So let's say that we did this in a container, all right? We got RMGX. I added another RX and MG. So let me write it down for you. I added this magnesium, this R, this X. What will happen is this RMGX is already in the solution. So X, Mg, and let's put this R over here. What will happen is this R would want to make a bond with this Mg. This X would want to make a bond with this Mg. This X would want to make a bond with this Mg. What would happen is this chlorine and R bond, the electrons from this would transfer to this. The electrons from this X and Mg would transfer to this. What would happen then? Well, as you might have guessed it, we would have R Mg X because of this, and another R Mg X. Oh my god, my handwriting is beautiful, because of this. So it catalyzed its reaction. See, they're extremely useful. So that was Grignard's reagent. The next two are organolithiums and I won't say the next name. It's deprotonating alkynes, but you wouldn't get why they're called that until I show it to you. So the next one is called organolithiums. Organolithiums. So do you guys know what organolithiums are? You don't? Well, the name suggests that it's ClIH3. It's the same thing we talked about when we were discussing the metal carbon bond. So how do we make this? Well, it follows the same reaction like the previous one. A special case of it is the Correa-House reaction, but the thing is, I won't show the mechanism of it. It's a similar oxidative insertion. What I will tell you is, let's take any random chain. All right, let's take this. I have chlorine over here. All right, we would need to react it with 2 moles of lithium in an ether solution. Let's take the ether this time as THF. What will happen is, one lithium will take the chlorine's place, and the second lithium would neutralize this chlorine. So once it takes the lithium's place, it would look something like this. The chlorine would, as a good leaving group, it would take the electrons and leave the reaction, or leave the compound. It will be like Cl minus. Now to neutralize this chlorine minus, the second lithium would come into play, and it will make it LiCl. So this is how you can make organolithiums. This chain can be anything. It can be benzene. Well, not benzene. That would be problematic. It can be any cyclo alkane that has, let's say, Br this time. All you need is 2 lithium and a THF solution. I hope you're writing this with me if you are actually trying to learn. I don't know why you're here if you are. So it would make something like this. Li and Br and Li. All right. This was how to make organolithiums. The third one is the most useful one, and it is the most important one too. All right. So this way of making organometallics is called, the new one that I'm going to tell you is by deprotonating alkynes. All right, deprotonating alkynes. I need to take a piss. Hold on. All right, I'm back. So deprotonating alkynes, right? What do I mean by deprotonating? Deprotonating means removing a proton. How do we show a proton in a chemical reaction? By writing it as like this. We'll write H plus. That means a proton. So we'll need to remove an H plus ion from this. How would we do this? Let's take an alkyne. What is the simplest alkyne? A 2-carbon alkyne is called an ethyne. All right. So H, and 2 carbons have a triple bond. What we will do is we will use an organometallic reagent to start the reaction. So let's take butyl, which has lithium at its end. Bu stands for butyl. What is a butyl? CH3, CH2, CH2, CH2. All right, that is a butyl. So what will happen is this time, see, it comes into play. The bond will send the electrons to this carbon, and the hydrogen would leave. It will deprotonate. So it looks like this. Hydrogen over here, 1, 2, 3, and the lithium. And this is an alkynyl lithium. So the alkynyl in this is ethynyl. So ethynyl lithium. All right. I'm really bad with names of organic compounds. So yeah, why is this important though? Well, it's not just you can use any alkyne you want over here. I just took the simplest one because it's easier to draw. Why are they important? Well, I'll show you why they're important. Let's see. Let's take ethyne again, all right? Hydrogen over here, hydrogen over here. Let's react it with a BuLi, all right? The hydrogen then, okay, I'll show it to you in this. The electrons would attack this carbon. The hydrogen would leave as the H plus, all right? We show this arrow for well, we use, okay, Jesus Christ. This arrow just shows the side products that are formed and it's not needed in the reaction, all right? So what will happen is it will replace that hydrogen. So it would look something like this. And Li is over here, all right? Now, this hydrogen would be neutralized by this Bu and it would form a butane, all right? Butane. Now, what we need to do is we will use this to attack 1, 2, 3, 4, 5, a pentane that has a ketone group on the second carbon. Comment the name if you know or not. I don't even know if anybody will watch this. So I told you how it will attack, how any nucleophile would attack the electrophilic carbon on this, right? So the lithium would attack it like this. The carbon lithium electron would attack it like this. The electrons would shift on the oxygen and you would get something like this. Bow, bow. And we will add an H plus to this so that the negative charge on it would be neutralized. All right. So it would look something like this with an OH over here and 1, 2, which has this. This is what we will get. And do you know what this is called? It is erythronolide A. Erythronolide A. I think that is what it's called, right? All right, yeah, I was correct. It is called an erythronolide A, and it is an antibiotic. Antibiotic. Now, what is an antibiotic? It is a drug or med or whatever you call it, pills. It's something that you take when your body's not feeling well. Speaking of bodies, there's another thing. If you are a girl, which is really less likely, why are you here? What the fuck? Am I that pretty? No? Okay, I'll go kill myself. So, you would be producing this if you're a girl. Alright? This is estrone. Does this look right? Yeah, it is. I hope. Yeah, it is correct. This is called an oestrone. Holy crack, I'm cracked, bro. Holy crap, I'm cracked. You see the spelling? Hell yeah. So, what we'll do is, if you don't know what estrone is, this is a sex hormone. It's not the same as estrogen, it's different. But estrone is also a sex hormone, and it is produced in females, alright? It's weaker than estrogen, that's all I know. So what we'll do is, we'll take the alkynyl lithium in excess, alright? That means we'll take a lot of these alkynyl lithium, the ethynyl lithium, and we would put it in a solvent that will give it H plus, and which would give it H2O. So what would happen is the benzene would remain unchanged. Well, can you predict what would happen? What do you think is the electrophilic uh, thingy in this, electrophilic center in this? If you said this, then you're correct. Well, try to draw the product before I do. It will attack this and then this will go up. I told you why that is important. So, if I can draw. And this. So, what would happen is that this pi bond would break. It will get a negative on this. The H plus would neutralize this, and it would look something like this. So, this wedged methyl stays the same. There will be an OH this time over here, and that OH would be wedged. OH. By wedged, I mean that it will be towards you. And this thing, this ethynyl chain, would be away from you. Like this. It would be away from you. So we inserted an alkynyl. Alkynyl, yes. So, and this is called, Jesus Christ, ethynyl estradiol. Holy shit, I'm cracked, yo. Yeah. Holy crap. Okay, I'm autistic. I'm sorry. So, diol is for 2 oxygen. Ethynyl is for the added alkynyl chain, and the oestra is from this. So, yeah. What is this? I did not tell you. This is a contraceptive, the birth control pills. So, contraceptive. So yeah, this is a really important reaction. The deprotonating of alkynes to make organolithiums, alright? No, not yet, this is also important, but I was talking about this. Deprotonating alkynes to make organometallics. So yeah, moving on. Now that I'm realizing the last bit was a lot, I don't think I should. I'll include it in the video. I don't care. So what was I saying? Yeah, let's take propane. All right, we will halogenate it with iodine. All right, it will be a controlled halogenation so that it would attach itself over here to the terminal. Now what we'll do is we will put Mg and THF. Do you know what it will make? If you said Grignard's reagent, then yeah, you're correct. So we have this, all right? We went from propane to making this Grignard's reagent. Now, what we will do is we'll take this and let's see what we can do with this. All right. So let me draw this. I'll write 1 over here. 1, 2, 3 MgI. So let's take carbonyl compounds for this one. What is the okay? Let's take aldehydes. What is the simplest aldehyde that you know? If you said aldehyde with a single carbon, then you are correct. It is called a formaldehyde. Jesus Christ, my hair is getting long. So the thing with formaldehyde is it looks something like this. Double bond O. What is the stance? It has an H over here. It has an H over here. So what will happen is this would attack this carbon in the pi star. Electrons would go over here and it would form this carbon with a single O, negative, hydrogen, hydrogen, and 1, 2, 3. All right. Now this negative charge is not good. All right. We don't want that. So what we will do is put it in an acid or anything that will give it H plus to neutralize this negative charge. This step is called quenching, or an acidic workup, WU. All right, it's called an acidic workup. So what we will get is 1, 2, 3 attached to this carbon and a OH with 1 and 2 hydrogens. So if you look at it, we went from propane, we made a Grignard's reagent, and then we made an alcohol. And this is a 1 degree alcohol. 1 degree. Why? Because it is attached to a carbon, a single carbon. It's not in between anything. So this is a 1 degree alcohol. What if we make it react with an aldehyde that is not the simplest one? Let's make it react with an aldehyde that has 2 carbons. So like this, and this will have an H over here, double bond O. Similarly, this will go over here, this will go over here, and we would do the quenching of it by giving it an H plus, and you would get OH over here, and this would be 1, 2, 3. 1, 2, 3. And this will be the hydrogen. So if I write it a bit more properly, it would be 1, 1, 2, 3, and the OH. So we made another alcohol. But do you know why this alcohol is different? Because it is a 2 degree alcohol. Yep. Why is it 2 degree? 1 and 2. It's the carbon that it is attached to has 2 carbons attached to it. So it is a 2 degree alcohol. Now, let's try a ketone, right? Let's try a ketone. So, MgI. And I want you guys to do it. If you're watching, that is, I want you to do this one. Okay, I hope you paused it and did it, or else I would have looked like a retard. And then we would quench it. What would happen? Oxygen would get an H over here. 1, 2, and 1, 2, 3. 1, 2, 3. This is the easiest way to show it. We have another alcohol, but this time is the 3rd degree alcohol. All right. Another compound that has a carbonyl group. Let me think. Okay. Oh yeah. Let's okay. Let's do this. MgI, and it has this. All right. Okay. Let's okay. Let's make it react with CO2. All right. I'll tell you what happens. What will happen is it will attack this, and electrons. Well, this would move up here. Even this could be done because they're symmetric, but for the sake of the example, I'll say that the above one will attract the electrons towards itself. All right. So what would happen is C, O, double bond O, and 1, 2, 3. 1, 2, 3. It will look something like this. And this will have a negative charge. We will then work it up with H3O plus, which will give it an H plus ion or a proton to stabilize it. And in the end, we will have 1, 2, 3. This carbon would have an OH over here and a double bond O. So do you know what this is? This is a carboxylic acid. Yeah, carboxylic acid. So this is how you would go from propane to a halopropane to a Grignard's reagent, and from that you could either make a primary alcohol, a secondary alcohol, a tertiary alcohol, or a carboxylic acid. Yeah, I think that's it. Oh, I have two more things to show you. Two more ways of making organometallic compounds or reagents. Alright, the last two that I'm going to show it to you is halogen metal exchange and transmetallation. Halogen metal exchange is really simple. I'll write it down. Halo M, okay? It means halogen metal exchange. What will happen is, let's say we have a benzene ring that has iodine over here, alright? We will take another, let's say, organolithium this time. What will happen is, this lithium would attack this carbon, iodine would leave, and we would have Bu. Bu is for butyl, alright? Bu would form a bond with the iodine, and we would have a benzene that has lithium attached to it. This is a halometal exchange. The other one, the transmetallation, alright, that is important for synthesis. Transmetallation. I hope that's the correct spelling. Alright, so let's take a benzene that has iodine in its meta position. What will happen is, we'll first make it react with magnesium and THF. So we got a Grignard's reagent. Alright, MgI. Now you're like, yo, what the fuck? It's the same thing. What's new about this? Why is it called transmetallation? Well, listen, alright. What we'll do now is change this whole thing with a more electropositive atom, alright? Element or a metal. And they are transmetals. So you have the name transmetallation. How we'll do that is by taking zinc with bromine attached to them, ZnBr2, alright? And another ether solvent, Et2O. What will happen is, this will replace this whole thing. So it would be something like this. You'll see that the Br, this is only a single Br, this is Br2. Well, zinc made another bond with this, so it had to get rid of one of the Br, and halogens are great leaving groups, so a Br just left, alright? So yeah, I guess that's it for this video. If I'm not feeling sleepy, I'll make another one, I guess. But yeah, that's it. Bye.